Hey guys, welcome back to my channel. Today let's talk about 千呼万唤始出来的 the maximum likelihood estimator. Maximum likelihood estimator. When we do low J regression or probability regression or the regression with a binary dependent variable, we know that all the coefficients are not called least squares estimators. Instead, they are called maximum likelihood estimators. So today's video will talk about how to derive maximum likelihood estimator and the most intuitive understanding of maximum likelihood estimator. MLE. Okay, without further ado, let's get into the video. Okay, let's talk about maximum likelihood estimator, MLE. So as the name suggests, you want to maximize a likelihood function. We know OLS, right? Ordinary least squares estimator. We minimize some error squared. Right, so let me give you a comparison. OLS estimator, so we just minimize some error squared. You solve for all the coefficients estimator, B0, B1, B2, for example. We call this OLS estimators. But for a maximum likelihood estimator, we just solve a maximization problem. So instead of minimize something, right, we maximize a likelihood function, or we maximize a likelihood, and we solve for the coefficient B0, B1, for example, and we call this maximum likelihood estimator. So now let's look at this likelihood function inside this parenthesis. We want to maximize the probability of something. We call this likelihood function, and you can solve for B0, B1. Okay, you can solve for B0, B1. So now, to be more intuitive, let me give you the data. So let's suppose the data is this each observation, 1, 2, 3, 4, 5, 6, 7. You have Y, this cross-sectional data, right, obviously. So that's Y1, Y2, Y3, Y4, Y5, Y6, Y7. We know Y is a binary variable, right? So this binary variable could be either 1 or 0. So that's maybe this is 1, this is 1, this is 0, 1, 0, 0, 0. For example, this is a Y variable, dependent variable is binary, okay? And X could be continuous. For example, X1, X2, for each observation you have the value of X, like this. So this is our data, right? Data set. Y is binary variable, X is continuous, or either binary or continuous variable. So now this likelihood function inside is a joint probability. So let me write here. So is a joint probability. So it's a probability of getting the value of Y you observed. I say probability that you observe Y1, which equals 1, and intersect, right? Intersection. So this means intersect or intersection. We find the joint probability. So that happened at the same time. So and you observe Y2, and you observe Y3, and all the way to Y sub n. So we want to maximize this probability of getting all the data you observed. Or we want to maximize the probability that we get all the values of Y we observed. Okay? What the probability that you observe Y1 equals 1, and Y2 equals 1, and Y3 equals 0, and Y4 equals 1. Okay? And the last variable maybe equals 1. So we want to maximize the joint probability. And because normally we use simple random sampling, right? Simple random sampling method to get all the observations. That means the observations are independent of each other, or we call IID, independently, identically distributed. So now they are independent, or the values of Y are independent of each other. So let's just focus on this probability, joint probability. So now we can write this as probability that you observe Y1 times, because it's joint probability, the multiplication, and probability you observe Y2, because they're independent, so you can write this way, right? And probability you observe Y3 times all the way to the probability you observe Y sub n. Because observations of Y, the values of Y are independent, so the joint probability can be written as this way. Okay, this is a likelihood function. So now you want to know what is the probability of y1, right? What the expression? How do I write probability of y1? How do I write probability of y2? So in order to write the equation or expression for the probability that y equals any value, you should know this thing. So you should understand this. So you should know this in order to expand this likelihood function. Let me give you an example. Let's suppose y, right? We know that a y can take on two values, right? 1 or 0. And the probability that you observe y is 1, maybe is p. And the probability you observe y is 0, and then you can write 1 minus p. Now we can write this way. So probability that y is 1, you know that is p, is given. And the probability that y is 0, you know that equals 1 minus p, right? Is given. And now we want to generalize this equation. We can write this way. Probability that you observe y equals a value, just y equals a value. We call it y sub I. It could be 1 or 0, okay? And that equals p to the power of y sub I, the value of y, times 1 minus p to the power of 1 minus y sub I. Now this is important because we need to use this to expand this likelihood function. So now we can verify this, whether we can get the correct probability of y. Okay, so let's suppose y equals 1. And now probability that y equals 1 equals, we just plug y equals 1 into this equation. You solve that, equals p to the power of 1 minus p to the power of 1 minus 1, which is 0. So the whole thing equals 1, equals p. And you see probability y is 1 equals p is here, right? And probability, for example, y equals 0. And now you can solve for probability that y equals 0 equals p to the power of y which is 0, and times 1 minus p to the power of 1 minus 0, which is 1. So that equals 1 minus p. You see, that's the probability that y equals any value. And here we know that y is binary, so it could be either 1 or 0. Okay, and now this p, what is this p again? This p is probability y is 1. So we can generalize this formula or this equation even further. So we have this probability that y equals a value, either 1 or 0, equals, and now this p, we know the p is the probability y equals 1, right? This p is the probability y equals 1. So now we can write this. Let me just use this color. So probability that y is 1. Probability y is 1 to the power of y times 1 minus probability y is 1 to the power of 1 minus y. So now we just use this equation to solve for probability y is 1, and then we'll plug this p of y back into this likelihood function. Okay, so now what the probability you observe, y1, that equals, use this equation, that equals, let me write here, equals probability that y1 is 1 to the power of y1 times 1 minus probability y1 is 1 to the power of 1 minus y1. So that's the probability y equals y1. And then times probability y equals y2, which is probability y2 equals 1 to the power of y2 times 1 minus probability y2 equals 1 to the power of 1 minus y2. Right? That's the probability you observe y2 equals a value, which is y2 could be either 1 or 0, right? And times all the way to the last term is probability that yn is 1 to the power of y sub n times 1 minus probability yn is 1 to the power of 1 minus y sub n. That's the joint probability or likelihood function. And see, now let me zoom out a little bit. I'm just using it right here. So now you see probability y1 is 1. probability y2 is 1 all the way to probability yn is 1. So you know what the probability y1 is 1. You know what the probability that y is 1 because you have this model. So you have the data here. You can use x to estimate the probability y sub I equals 1. You can use either logit or probability model. Let's suppose we use probability model, for example. So now you have this, we use probability model or logit. Right? So now you have this y hat predicted value of y, and we know predicted value of y equals expected value of y given a value of x. And because y is binary, we know that that equals probability that y is 1 given a value of x equals phi of, because it's probability model, so it's based on cumulative standard normal distribution functional form. Right, so that's b0 plus b1 x sub I. That means we can use this x, the value of x, to estimate the probability that y equals 1. Right, so now you use this. Let me move up a little bit. So you have this term, right, equals phi b0 plus b1 x1. So this is probability that y1 equals 1 given a value x1. The same thing, phi of b0 plus b1 x2 equals probability that y2 equals 1 given value x2. All the way to phi of b0 plus b1 x sub n equals probability that yn equals 1 given a value x sub n. Now you know the probability y equals 1, y1 equals 1, y2 equals 1, all the way to y sub n equals 1. And then we can plug this back into this equation. So now we have this. So the likelihood function is phi b0 plus b1 x1 to the power of y1 times 1 minus phi of b0 plus b1 x1 to the power of 1 minus y1. Okay? And times probability y2 is 1, phi of b0 plus b1 x2 to the power of y2 times 1 minus phi of b0 plus b1 x2 to the power of 1 minus y2 times all the way to the last term, which is phi of b0 plus b1 xn to the power of yn times 1 minus phi of b0 plus b1 xn to the power of 1 minus y sub n. You want to maximize this whole joint probability. And you see, you know the value of x1, y1, x2, x1, y1, x2, y2, x2, y2, all the way to xn, yn, because you have the observational data. You have the data here. You have this x1, y1, x1, y2, x2, y3, x3. So you have all the data. So now you can plug all the data into this joint probability, and the unknown variables are b0, b1, b0, b1. So you just solve this maximization problem to get the value of b0, b1. That means you need the value b0, b1. You can try different value b0, b1 until you get a value b0, b1 that can make this whole joint probability maximized. Okay, so this b0, b1 can maximize the probability that you get the data you observed. Again, the value of b0, b1 can make you maximize the probability of getting the values of y that you observed. Okay, so that's, you maximize this whole joint probability, you get the value b0, b1. For example, b0 is 4, b1 is 5, just an example. And we call this maximum likelihood estimator for the corresponding population parameter beta 0, beta 1. Okay, because we maximize a likelihood function, so we call this maximum likelihood estimator. Okay, and for OLS, we minimize error squared, right? We call this least squares estimator, but here is called the maximum likelihood estimator. Yeah, that's how we solve for it. In practice, we never do it by hand. We won't do probability logit model. For example, we just use computational software like Stata or Python. You can get the b0, b1, which is maximum likelihood estimator. So using the software, you can easily get this B0, B1 maximum likelihood estimators. Here, we only have one regressor, so this is B0, B1. If you have more than one regressors, you have B0, B1, B2, okay, or B4. So that's maximum likelihood estimator. I hope you find today's video helpful. And so any questions, comments, please comment down below, let me know. And thank you so much for all the questions. Give me a lot of inspirations, give a lot of video ideas, and so have a good holiday season, and I'll see you in my next video. Bye.